Welcome to this Forged College Explainer. Today we're actually taking Bitcoin mechanics straight out of the textbook and bringing them right into the laboratory. We've talked a whole lot about the theory behind SegWit and Taproot, but let's be real, theory only gets us so far. In this explainer, we're going to run a hands-on lab experiment to see exactly how these protocol upgrades translate into real, practical privacy effects for everyday users. We really want to know what your transactions actually look like when they hit the blockchain. So let's dive right into this. I want you to imagine this explainer as a bit of a detective story. On one side, we have you, the user, just trying to maintain your financial privacy. And on the other side, we have an overly enthusiastic digital snooper. You know the type, someone constantly analyzing the public blockchain, trying to connect your real-world identity to your wallet balances and your spending habits. Today, we're going to run a highly controlled A/B test to see if our on-chain footprint can actually outsmart that snooper. So, can anyone track your Bitcoin? Let's find out. Here's our agenda for the lab protocol today. First, setting up the lab. Second, Demo A, which is our SegWit baseline. Third, Demo B, exploring the Taproot disguise. Fourth, checking the privacy results. And finally, number 5, practical limits and takeaways. All right, Section 1, setting up the lab. Okay, before we start firing off transactions, we need a controlled sandbox where we can safely generate evidence without risking, any actual funds. To do this, we're going to fire up a Bitcoin core node, but we'll run it in regtest mode. If you haven't used it, regtest is basically a local testing environment where we control the blocks and, crucially, the fake money. It's real science, but with zero financial risk. Once we've got regtest running, we create 2 descriptor wallets, one for our older SegWit transactions and one for our newer Taproot tests. Finally, we just mine some local blocks to fund these test addresses. And boom, we now have UTXOs, unspent transaction outputs, ready to be spent in our little experiment. But before we run the tests, we kind of need to understand our adversary, right? Our on-chain detective relies heavily on something called a clustering heuristic. Now, just think of a heuristic as a basic rule of thumb. Observers use these analytical methods to link multiple Bitcoin addresses back to a single owner. They're basically looking for digital breadcrumbs. For example, if you spend a $10 bill to buy a $3 coffee, you get $7 back in change. On the blockchain, that change goes to a new address. A clustering heuristic tries to identify that shared change output and deduce that the inputs and the change address belong to the exact same person. This is the specific snooper we are trying to defeat today. Moving on to Section 2, Demo A, our SegWit baseline. So this is our control group. We want to see exactly what happens when we use standard SegWit version 0, which, as you know, has been the industry standard for several years now. For this baseline setup, we construct a transaction that spends 2 standard SegWit inputs, technically known as pay-to-witness public key hash inputs. We're making a payment to a target address and then returning the remaining funds back to our own wallet as change. To do this securely, we use a PSBT, a partially signed Bitcoin transaction, to build it, sign it, and finally broadcast it out to our regtest network. Now, let's look at the decoded result of that transaction. When we run a raw decoder, the snooper sees absolutely everything we just did. They see those segregated witness arrays for each input, but more importantly, they see an explicit change output that very obviously matches common change heuristics. Because of the way this transaction is structurally built, the detective can easily cluster those inputs with the change output, successfully mapping out our wallet behavior. So in this round, the snooper definitely wins. Look, SegWit improved a lot of things by moving signature data into the witness, but it absolutely did not inherently break clustering based on change outputs. All right, Section 3, Demo B, the Taproot disguise. Now it's time to bring in the heavy artillery. We're running our highly anticipated upgrade test using Taproot to see if we can finally shake off this snooper. For this demo, we're actually testing 2 variants of Taproot spending. First, a standard single signature key path spend. This is just your regular everyday payment. Second, a much more complex script path spend. A script path allows you to commit to a complex script tree, think something like a multi-signature requirement or a time lock, without broadcasting all those complicated rules to the entire network up front. And man, this brilliantly illustrates the real power of Taproot. When we decode the key path spend, the snooper finds almost nothing useful. Instead of complex scripts, they just see a single, uniform Schnorr signature sitting right there in the witness stack. There is absolutely no separate script public key revealing your spending conditions. So, to the snooper, your transaction looks identically uniform to literally millions of other single-signature Taproot spends. It acts like a perfect digital disguise.
But here is the major aha moment of Taproot, especially when it comes to the script path. If you have a complex multi-signature setup or some obscure time lock condition, it remains a total secret from the network. Those specific conditions are only revealed in the witness data when that specific script path is actually executed. Meaning, if you never use the backup script, the snooper never even knows it existed in the first place. They just see what looks exactly like a standard key path spend.
Okay, let's get into Section 4, checking the privacy results.
So, the big question, did we fool the detective? Comparing our findings head-to-head, the absolutely crucial point is mapped out right here. In Demo A, utilizing SegWit version 0, our primary mechanism was witness separation. Now, that was great for protocol efficiency for sure, but as we just saw, it left us totally vulnerable to change heuristics. The snooper could easily link our activity. In Demo B, utilizing Taproot, our primary privacy mechanism was keypath indistinguishability and script commitment. By making standard spends look completely uniform and hiding complex scripts until they are actually used, we drastically reduced the metadata available to our snooper. Let's see how this builds a really stark contrast. Demo A essentially handed the detective an easy map to follow, complete with explicit linkable change outputs. But Demo B, it forced that exact same detective to stare at a massive, unreadable sea of identical Schnorr signatures. When your transaction looks exactly like everyone else's, that clustering heuristic completely loses its power. Which brings us to Section 5, practical limits and takeaways.
Okay, but before we declare total victory over blockchain surveillance, it's time for a very necessary reality check. The absolute most important takeaway from this entire explainer is this. On-chain privacy is not a magic toggle switch. Indistinguishability is not binary. Taproot provides us with some truly incredible tools, but it is highly, highly dependent on user behavior and wallet design. If your wallet handles change poorly, or say if you practice sloppy behavior like reusing the exact same address over and over again, structural heuristics will still work. The detective will still catch you even if you are using Taproot. Therefore, we really have to view these privacy gains as incremental and deeply context-dependent. Taproot gives you the ability to blend into the crowd, but you still have to act correctly to actually stay hidden. Which leaves us with this final, crucial thought. If privacy truly is an incremental game of inches, what habits are you leaving on-chain today? Are your current wallet practices giving the snoopers exactly what they want? Or are you utilizing protocol upgrades like Taproot to actually protect your financial footprint? Well, that wraps up our hands-on lab for today. I really hope this Forge College explainer sheds some light on the very real, user-centric effects of these massive protocol upgrades. If you want to dive deeper into this topic, maybe run these code exercises yourself or explore other fascinating Web3 concepts, I highly encourage you to visit forge.college for some incredibly detailed educational resources. Thanks so much for exploring with me, and keep learning.